Hey, before we go any further, I need to clarify two different meanings of concentration in solutions. Concentration of what? What we call a solution concentration or a species concentration. The first of those, a solution concentration, is what we put on the label of a reagent bottle with a solution in it, or the labelled concentration. The species concentration refers to what are the concentrations of the species in that solution with that labelled solution, labelled concentration. Okay. Suppose and the symbols we use for these is a little c, and for the species concentration it's a square bracket with whatever the species is that we're talking about inside the bracket. Let me just try to demonstrate by some examples rather than giving you definitions. Suppose I had a 0.10 mole per litre sucrose solution. The labelled concentration, with what we'd put on the bottle, would be 0.1 molar sucrose solution. That's the solution concentration, or the labelled concentration, is little c of C12 H22O11 is 0.100 moles per litre. Now, sucrose is a non-electrolyte, so all of the molecules of sucrose that we put in there remain as such, none of them ionise, and we can now say the actual concentration of the species. By species we mean any molecules or ions that are in solution. Because these stay there as such, we can also say that the concentration of sucrose molecules, that's 11, is 0.10 molar. They're the same thing. Okay, now that might seem a little bit trivial, but suppose we made up a solution 0.10 molar potassium sulfate by dissolving 0.1 of a mole of potassium sulfate in water and making it up to 1 litre, or something in proportion to that. Then straight away, what do we put on the bottle? We say we put on the bottle a label, that label, and we're now talking about a concentration, a solution concentration of K2SO4 is 0.10 molar. But this is an ionic compound, and when we put into solution, the ions separate. They don't separate of their own. They separate as a result of water molecules grabbing those ions and pulling them apart. And this happens, K2SO4, when it dissolves, forms, each one of those forms 2 potassium ions. I shouldn't say each one of those because they aren't there as individuals, they're as a lattice work of potassium ions and sulfate ions, but on a one-to-one basis, and sulfate ions with water molecules around them. Now, what's the concentration of the species? Sorry. K2SO4 in this solution. Yeah, correct. There are none of them. Although we have a solution we made by putting potassium sulfate in water, but there is no potassium sulfate as a species in that solution. That's 0. It's all gone, and it's been changed into these ions. So now we can also say the concentration of this species, K plus ions, are twice as many of them as there were moles of that, is going to be 0.20 molar, and the concentration of sulfate ions, 1 produces 1 on a molar ratio, will be 0.10 molar. Okay, so that's the first time we can see that there is a distinction between the concentration of the species and the label concentrations. Suppose we had a 0.10 molar HCl solution. I'm now talking about not an ionic compound, but a molecular compound, HCl gas dissolved in water, sufficient to make up the concentration, sufficient that we have dissolved 0.1 of a mole of hydrogen chloride in water, made it up to 1 litre. The bottle label is such that the solution concentration is 0.10 molar, but HCl is a strong electrolyte, so we can now straight away say that the concentration of HCl, we put HCl in, but there is none there anymore. And concentration of hydrogen ions is 0.10 molar, and the concentration of chloride ions is 0.10 mole per litre. Okay. Now, let me clean this. Okay. Let's now use the example of a 0.100 mole per litre solution of formic acid, or methanoic acid, you might call it, solution. We can straight away say on the bottle we would put the label that, and if we're writing a specification, we'd say that the solution concentration of that stuff is 0.100 molar. But this is a weak electrolyte. We've talked about that before. That means that some of it, but not all of it, ionizes. And it does so according to this equation, reaching a condition of dynamic chemical equilibrium, formate ions and hydrogen ions. Now, what can we say about the concentrations of the species in this solution? Some of this will have ionized by the time the concentrations reach a constant value in that condition of dynamic chemical equilibrium. So we can now say this much: the concentration of those molecules, that species, is going to be less than that. And for every number of moles of this that ionize, it'll form an equal number of moles of that and of that. So now we can say that the concentration of formate ions will be equal to the concentration of hydrogen ions equated, and all of those, both of those, will be something greater than 0 moles per litre. And at this stage we can't tell, but that's where we'll be going in the next session. Now you'll have to take my word for it that in fact at 20 degrees 4% of those molecules are ionized by the time it comes to equilibrium. And 4% of that is 0.004. So now we can say at equilibrium, in this solution, which arrives at equilibrium very, very quickly, the concentration of that molecular species is this, take away 0.004, 0.0096 molar. And the concentration of formate ions, which will be the same as the concentration of equated hydrogen ions, be 0.004 molar. So you can see it's now getting a little bit more complicated, the distinction between a species concentrations and the labelled concentration. Now, suppose we come to think about a 0.100 hydrogen fluoride solution. We can say straight away the solution concentration is, by the way we define it, HF, 0.100 moles per litre. But now at 20 degrees, 8% ionises. It's a weak electrolyte, but different weak electrolytes ionise to different degrees. They are differently weak or differently strong. And if that's the case, then in this solution, the concentration of HF is 0.092 moles per litre. The concentration of hydrogen ions equated and the concentration of fluoride ions equated is 0.008 moles per litre. All right? So I hope you're getting the gist through examples of the distinction between these things. Now, why does this matter? Because in chemistry, there are lots of mathematical relationships that involve the concentrations of solutions. And in those mathematical relationships, it's the species concentrations that we use, not the labelled concentration, because this only tells us how we made it up. These things tell us what is actually in there. Okay? So for example, just foreshadowing where we're going, in the next session, if we have a solution of methanoic acid and we know the equation of its action as a weak electrolyte, we can define, as we have done in other conditions of dynamic chemical equilibrium, a thing that we give a symbol Q to, which is the concentration of species on the right-hand side raised to the power of the coefficient here, which happens to be 1, times the other species on the right-hand side raised to the power 1 over the concentration of this species, molecular that, raised to the power 1. And in aqueous solutions, no matter how they're made up, involving those species, always the value of this product is equal to some constant value given the same temperature. Right? That's the law of equilibrium. For example, in a 0.1 molar solution of this, if C of formic acid, methanoic acid, is 0.100 molar, remembering back the this value of Q now is the concentration of this, I think, was 0.004. The concentration of this was 0.004. The concentration of this was 0.096. And whatever that value that is, I think it's something like 6 by 10 to the minus 4. I'm not sure. You can quickly calculate that. And whatever that is, it's the same in every solution containing those things, no matter how they're made up, if it's at 20 degrees. And that understanding, that distinction of what these species concentrations are, is what we're going to need in our next session. Okay, any questions? Yeah, a little bit bamboozled by it. think about it. Hopefully it'll make more sense when we start applying these tomorrow. Okay?